Welcome. I am a master's student of Advanced Computer Science, and today I will be speaking to you about my project. Let's begin. As you know, the traveling salesman problem is a very famous problem within computer science. The Hamiltonian path is one where each vertex can be visited only once, and the problem I'm focusing on is about finding the second Hamiltonian cycle in a cubic graph. It's an NP-hard problem as described in Karp's paper. The best algorithm for it is an exponential time algorithm, Thomasson's lollipop algorithm, with an update by Samaraev, Spirakis, and others. It works in the following way. First, we have the cycle as given by removing one edge, which we color red. We achieve a path. Then, by taking another edge of the last vertex, we color it blue, and then we break the lollipop by coloring another edge red. We can nicely spin it out to create a line again via reordering, and continue in the same manner by looking at the last vertex, coloring an edge blue and breaking the lollipop. The worst case takes 1.23103 to the n time within linear space selection. As you can see, it produces a circular alternating cycles graph, as seen here, which can be visualized in different ways. I've read up in various literature to deepen my understanding of graph theory and relevant topics. To summarize it, Smith's theory about even number of edges led us to Thomasson's practical implementation of the algorithm, then Kravchik's family of graphs on 8n plus 2 vertices where n bigger or equal to 1 led to Cameron's proof that Thomasson's algorithm is in fact exponential on this family of cubic graphs. Spirakis and Samaraev answered the question, does the knowledge of the first Hamiltonian cycle, CO, strictly help to reduce the running time of the lollipop algorithm, with a yes. And we've also been given a reduction by Zong that if we have a polynomial algorithm for finding a second Hamiltonian cycle in a cubic cyclically 4-edge connected graph, that there must exist a polynomial algorithm for finding a second Hamiltonian cycle in any cubic graph G. Which of course is my biggest goal to facilitate in finding this polynomial algorithm. I decided to make the project a web application to help more researchers understand this algorithm without the necessity of downloading anything. It will work on a website interactively. I've made some decisions on what stack to use, with SQLite for the database, Django for the backend because it uses Python, which is so widely popular that even researchers from different disciplines such as mathematics or engineering can use. And for the front end, I decided on Facebook's React framework, which uses JavaScript, the most widely used web scripting language. I've also thought about the visualization being in 3D, but decided that it would be simpler to do it in 2D, especially as most, if not all, of my graphs will be planar graphs. I've also thought about the visualization being in 3D, but decided it will be simpler to do it in 2D, especially as most, if not all, of my examples will be looking into planar graphs. I've also thought about some domain names. Here you can see a graph. Initially, I plan on the user to be redirected to the Thomasson's algorithm page, where the experiment settings show up. Then the user can view three things: the code line by line, the console, and the visualization, with options like pause on breakpoint, and when the run finishes, statistics are displayed. Then the user has an option to download those stats or send to email or to press compare, being taken onto a list of all experiments, where the user can select multiple and view the stats comparison page. For example, a line graph would have a few lines of those different experiments compared. Here we have the initial class and function overview, where you can notice the kind of methods within Thomasson's algorithm. For example, those include lollipop, find Hamiltonian cycle, verify Hamiltonian cycle, path reorder, make graph, update code text with relevant graph and cycle data. Here we have the interface design sketches. As you can see, the page structure at the top, with the yellow box being the experiment settings, slide over that displays at the beginning. This shows the design of a person inputting their own graph and cycle, either by pasting in their vectors or being able to select the vertex count. Then, when the table appears, to select the edges, with at first the button being magic fill, where those can be finished up at random, or when the table is complete, the finish button. Of course, X's appear automatically after 3 edges are selected per vertex, and there's automatic symmetry. I'm not using test-driven development, where you write the tests first and then fulfill the criteria with code. Rather, I code first, test later, but of course everything will be tested to work as intended on different screen sizes, systems, and browsers. From my initial testing that I've done, and general idea influenced by papers with different patterns and types of graphs, I decided for my main research hypothesis to be measuring precisely the kind of time complexity that can be expected from those different types. Being able to predict those times based on the graph and notice the kind of graph that produced the worst time case of Lollipop's running time, to possibly amend it and make users aware of their limitations and the kind of graphs it works optimally on. The first experiments are based on Cameron's paper as shown here. There's one graph with 10 vertices and another where 2 of those graphs are connected by 3 edges. Next experiment is Zong's 4-edge connected bipartite graph. As you can see, the structures, there are 4 shortcut edges within it and form slightly longer shortcuts. The next part is when the user can input their own graph, as I already mentioned. And the last part is the graph generator, where there will be a database of various graphs that will be separated into different categories. And the way the generator works is by letting the user select the pattern type and the vertex count, to then start with initializing the matrix of zeros, then updating it with a selected pattern, and then the random fill takes place until each vertex has 3 edges. Then, to be verified, it contains a Hamiltonian cycle that can be our first input cycle, else it repeats the process from the beginning. However, according to the research I've done, there are substantially more cubic graphs with Hamiltonicity than non-Hamiltonicity. However, I will look into how to make this into the best kind of generator possible. So some of the different types are 5-edge connected or 4-edge connected graphs with either few or many cycles. There's of course the kind of generalization as can be seen in figure 7, where any graph could be taken twice with only updating a few edges, so they are connected by 3 for instance. There are some more patterns here, and the experiment class structure will look something like this. The experiment can take the information either directly from the graph database or examples, or whether your input your own or use the generator. It will use the random fill method after using this pattern selected. Evaluation of the software will be done by myself, by the supervisor, and with some consideration of beta testers. The criteria will include ease of use, visual aesthetics, good amount of experiments which can be undertaken, and code clarity and structure. For the empirical investigation, I will be saving the results as I am conducting them, making some predictions on experiment iterations, and comparing results with those predictions. I'll be using a uniform distribution of samples, comparing certain types of graphs with each other, such as similar pattern graphs, and then the summary of each pattern against each other as well. Calculating different aspects in the process, such as variance, standard deviation, distance from the mean, and clustering the data to help differentiate different kinds of graphs from each other based on the iterations and running time. Of course, producing nice graphs in the process to easier understand and make conclusions based on the results. And of course, I anticipate having my hypothesis proven and be able to accurately describe why. So far, the main part for me was to immerse myself in the current research on the topic and plan my project implementation. I started making progress on 2 separate aspects of the project, one on the experiments from Cameron's paper and general implementation of Thomason's using alternating cycles algorithm in Python. As you can see, despite having some small errors within the Lollipop implementation, I produced a radar graph of iterations in figure 12, which helped me decide on the initial hypothesis. But I've also made a start on the design of the web page and made an API for it. For instance, here the code of experiment is just easy uploadable from the admin side I made. Of course, making it function now and visualize within the website rather than just in Python on your machine is the next step. Now I'm going to rewrite it into JavaScript and continue making all the different functionalities for different experiment choices. As you can see, I've started with research and planning, going into the red stage implementation, then with some experimentation results, hopefully I can write my own theories and proofs of the highest standard, hopefully of publishable quality. And the Gantt chart shows you what I focus on each week. For instance, I hope to have as much functionality as possible implemented by around 16th of August, where either that week or the next I want to release a beta version to get some reviews and suggestions for improvements. Here are some of the references, and thank you for listening.